All right, welcome everybody. We're going to be doing lesson 5 for the applications of derivatives section here as we continue talking about related rates. We're going to go ahead and just jump right in. We're going to have the same kind of objectives we had previous lesson. Yesterday, we saw that the rate of change of the volume of a sphere is related to the rate of change of the radius of the sphere. How does this work with other solids like cones? From oil leaks to sand piles to coffee pours, there's a lot to explore. So there's a lot for us to look at in terms of cones. The cone below has a height of 15 inches and a radius of 5. Let's go ahead and just label that on here. So we have a height of 15. So that is our height of this entire cone here, which is 15 inches. And we have this radius here, which is 5 inches. That's our R. Okay. When water is filled up to a height of 12 inches, so here we have our water level filled up to a height of 12 inches, what will the radius be? So we're curious what this radius, what this distance here. It's an excellent blue color to go with the water, but well, we want to know what what size that radius will be. Okay, cool. Turns out what we have here is a situation of similar triangles, right? You may remember this from geometry, but you'll notice each of these triangles has this right angle, and then they share this angle here in common. So we could call this angle-angle similarity for this smaller right triangle here. Again, this height being 12, this radius being our unknown. They are going to be proportional to the height and radius of our large cone here. So how do we kind of figure this out? We can set up a nice proportion, right? The radius of our larger cone divided by the height of our larger cone is going to equal the radius of the smaller cone divided by the height of that smaller cone. And fortunately for us, we can simplify one of these fractions to make this a little bit easier. 5 over 15 does simplify to 1/3. And when we do our kind of our cross multiplication here, we're going to get 3r equals 12, and divide both sides by 3. We can find that our radius will be 4 inches. So that is the radius of this smaller cone side right over here, or smaller triangle here, the cone of water. Again, how do we know this? This is based on similar triangles. And this is something that we can always do with these sort of cone problems. You'll see a lot of related rate problems that involve cones filling up or emptying. But again, the reason here is that we have similar triangles. All right, part B. When the water is filled up to a height of 10 inches, what will the radius be? Again, we can solve this in a very similar way, right? What are we changing in this proportion, right? If we're really just changing one value in this proportion, we're changing the height of that smaller cone. So we're going to get 1 over 3 equals r over 10. We do our little cross multiplication, right? 3r equals 10, divide by 3. And so r would be 10/3 inches, or 3.3 repeating 3 1/3, however you want to represent that. Again, based on the same proportion that we solved in the previous problem. The only thing that I'm changing here is the height of that smaller cone, that water level that we're dealing with. All right, now in general, right, we can kind of express a general relationship between the height and the radius in this situation, right? We know that the ratio of the radius divided by the height is always going to equal this constant in this problem of 1 over 3, right? That's our reduced version of 5 over 15. So if we do kind of a little cross multiplication again, right, multiplying and multiplying, we get 3r equals h, or that the height is equal to 3 times the radius, right? Height, that's not what I wanted to write there. That height equals 3 times the radius. Now we could also kind of flip this around a little bit and solve this same equation over here for r, right? If we divide both sides by 3, we get that r equals the height divided by 3. Or, if we don't like writing it in that way, we can always, write that in a slightly different way where the height is equal to 1, or the radius equals 1/3 of the height. So radius equals 1/3 times height. Oof, I am struggling with my spelling today. Anyway, radius equals 1/3 times height. Again, both of these equations could be useful for us. in various ways. When we're dealing with the volume of a cone, we may want to write that formula only in terms of radius or only in terms of height. So both of these give us nice substitution equations to use, right? If we want to replace h, we can replace it with 3r. Or if we want to replace r, we can replace it with 1/3 h. Again, both of these give us nice substitutions that we can use into our volume formula if we need it. All right, moving on down. Question 2 here says the cone is filled from above to the brim with water. Okay, again, we're kind of looking at a related rate situation, so it's always good to sort of draw a picture. So we have our cone. It's the same cone as before, so we know that the radius is 5 and the height here is 15. And it's filled all the way to the top with water, so all the way to the brim, all of this is water. Okay, and water is draining out of it, so we'll just say, water is draining out at a rate of 10 cubic inches, so 10 inches cubed per minute. So this is our water flowing out. Another way of thinking about this is our change in volume per time, right? Inches cubed is a volume unit. It's our filling up of that cone, and minutes, it's per time in this situation. So again, I can think about this as dV/dt. Write an equation that relates the variables in this problem. So we have radius, we have height, we have dV/dt. I'm not really gonna, do that, but volume. We want to write a volume formula that relates our height and radius. So the volume of a cone is 1/3 pi r squared times height. Right, that is just the standard volume formula for a cone, and that's what we're dealing with. We're dealing with a cone that's being filled up, so we're dealing with the volume of a cone. Part B, which variables in the above equation are changing? Which are staying constant? So this is kind of tricky, right? Because these numbers are not changing for our large cone, right? But as the water level lowers, right, say it gets all the way down to here, right, now this radius is going to be a different value. And this height would also be a different value. So as the water drains out of it, the radius is going to be getting smaller and the height is getting smaller. And throughout that whole process, as radius and height are both getting smaller, right, so is the volume, right? The volume is changing. So in this situation, all of them are changing, right? Volume, radius, height, they're all changing throughout this situation. None are staying constant. And this is a tricky concept for a lot of people, right? This idea that none are constant, because these numbers aren't really changing, right? The height and the radius of our original cone, but that's not really what we're looking at. In this scenario, what we're really looking at is we're looking at the cone that's created by the water. And as that water level lowers down, as more of it flows out, that cone is changing, all aspects of it, including the radius and the height and the volume. All right. How is this different than yesterday's problem with the helium balloon, right? How is this different? The problem yesterday, we had a volume formula like this, right? Volume equals 4/3 pi r cubed. That's our volume of the sphere. And you'll notice that our volume is only dependent on the radius, versus now we have a formula where volume is dependent on two things, which are both changing, right? We have both the radius and the height. So that's going to make a little bit of a difference here. Our volume is dependent on two different variables, or two different really functions, because those are going to be changing over time, versus our original problem from yesterday with our sphere. We had a sphere that was a balloon, right, and it was filling up. The only variable we had was a radius. Again, so that's going to make things a little bit trickier. Okay, let's see if we can rewrite the problem to look more familiar, more manageable. So we're going to rewrite our equation in 2a. So that's the volume of the cone equation that I have right here. But we're going to try to do it so that the volume is only in terms of radius. And so this goes back to something that I mentioned before. If we scroll all the way back up here to these two equations, right here and right here, So we have a way of replacing R or replacing H by using these formulas. So what we're going to do is we are going to be replacing H using this one right here. We're going to get rid of our H in our formula and replace it with 3R because that is a constant relationship that will always be true in our cone scenario. So we get V equals 1/3 pi R squared times 3R. Again, that is our replacement for H because using that proportion from earlier, we know that H is equivalent to 3R. All right, there's a little bit of simplifying. These 3's can actually nicely cancel out, right? 3 times 1/3 is just going to be equivalent to 1, and then we can also combine these R's together. So let's write out that in a little bit of a nicer way. We got V equals pi R cubed. Much nicer formula here, right? This is a much simpler one, and now this looks a lot like yesterday's problem, where our volume is really only dependent on radius. And actually, this equation is even easier than yesterday's because we were able to drop this fraction. All right, so let's take the derivative of both sides with respect to time. So we're doing the derivative with respect to the change in time of our formula here. Okay, derivative with respect to time. So derivative of v with respect to time, right? What is that going to be? That's going to be dv dt, which conveniently, remember, we do know that is actually equal to a constant in this problem, equals pi, which is a constant, right? We're not going to change that. And now we need to take the derivative of r to the third. That's going to be 3r squared times dr dt. Remember, anytime we're taking the derivative of these variables that are not time, we always need to add on times dr dt or times dv dt using the chain rule. Cool. We can clean this up, a little bit. There are some other ways of writing this, but I'm going to go ahead and leave it at this moment, just like this. Alrighty. Part C. At the instant when the radius is 4 inches, so we have r equals 4, what is the rate of change of the radius? Okay, so we are going to be looking for dr dt in this formula. Fortunately, we know dv dt. We know our radius. And yeah, that's all we need, right? All the other values in this formula are constants, so we should be able to now solve for dr dt. So that's going to be 10 equals pi times 3 times 4 squared times dr dt. All right, this side here can clean up a little bit. If I multiply that all out, right, we would get 48 pi. And we would want to divide this side of my equation by 48 pi to isolate dr dt. So we're going to get dr dt is equal to 10 divided by this side of my equation, 48 pi. So 10 over 48 pi. And we could also, kind of move forward with that and get a decimal value if we really wanted to. I'll go ahead and do it. Might as well. So I'm going to do this calculation. 10 divided by 48 pi, that's negative 0.066 inches per minute. Now, how do I know these units? And let's kind of talk about this. We are measuring the change in radius per change in time. Our radius is measured in inches, and our time in this problem is minutes. Again, we can kind of look at our dv dt up here, sort of help confirm that, right? Our measurement is cubic inches, so radius will be in inches, and our time unit is minutes. Again, similarly, our radius here is in inches when we're given that measurement. So that is our change in radius with respect to time. All right. Sliding on down. At the instant when the radius is 4 inches, what is the rate of change of the height? Cool. All right. So in this situation, how are we going to do this? Well, fortunately for us, we have a nice clean relationship between height and radius. We know that our height is equal to 3 times the radius. We could do this in a little bit of a more complex way where we rewrite our volume formula like we did up here, but instead of replacing h, we could replace R and have our equation where our volume is only dependent on H, but that's going to be a little bit more complicated than what we do. What I'm going to do is use this nice relationship we established earlier on. I'm going to go ahead and take the derivative of both of these sides, so with respect to time. And what we end up getting is that the change in height with respect to time is equal to 3 times the change in radius with respect to time, right? All I did was take the derivative of this h, remember h to the first power, so that's just going to be 1, or the h dt. And then derivative of 3r, again, really to the first power here, is going to be 3, remembering our dr dt. So the change in height is equal to 3 times the change in radius. So our change in height with respect to time is going to equal, again, multiply this value here by 3, and we get negative 0.198 inches per minute. Again, inches is our measurement of unit, just like radius, so inches per minute. Cool, right? Again, this is a simpler way of doing it than noticing this clean relationship formula that we had before and taking the derivative of it, but there are other ways that we could have gone about this. All right, so moving on down to a couple things we want to formalize, some important ideas. So we're going to talk about these cone problems. These are some relatively common problems that we may run into on the AP exam, and we'll definitely look at some more here together. So first step, and this is something that we did, is relating the radius and the height, relating radius and height using similar triangles. So this is going to be one of our first steps in a lot of these problems, is creating a nice equation that relates radius and height using the idea of similar triangles. As an example, right, what did we have? We had that 3r was equal to h. That was a very nice formula that helped us out. And again, we established that by noticing this proportion that we could write. And then by solving that proportion, we got this nice clean relationship. Okay, what is the second thing we need to do? Second thing is going to be very common. We're going to try to rewrite the volume formula, rewrite our volume formula, which I'll go ahead and write out here. Only using R or H. R or H. That's going to make things a lot easier. Now, that means replacing either R or H using our formula that we've established in this first step. Again, that gives us a volume that's only based on radius or only based on height, keeps things a lot more simple for us, right? Step 3, that's when the derivatives come in. We got to take the derivative of whatever formula, derivative, not derivative. So take the derivative of both sides. So we'd take the derivative of this resulting formula that we have up here. That would only be based on R or H. Finally, step 4, use the formula to solve for the desired quantity. Now, we have some other things, obviously, in this process that we're going to be doing if they're not provided for us, right? We're going to draw a picture if we need to. We're going to label that picture, label. We're going to identify variables, including any rates that we might know, like we knew the rate of change for the volume in that previous situation, right? There's a lot of things that are going to be good practice for related rates problems in general that we'll also do in this process. But these should really help us with these cone problems. In particular, these first 2 steps where we relate our radius and height using similar triangles, again, getting some formula like this, and then to rewrite the volume formula using only R or H. Those 2 things are going to be very key and crucial when we're dealing with these cone problems. Anyway, thank you all. I'll see you next lesson.